We would like to welcome everyone tuning in live, as well as anyone who has signed up for the webinar. This will be recorded, so if you have to leave or miss part of the webinar, don't worry, it'll automatically be sent to the email that was used to register. If this is not your first Multimechanics webinar, we're glad to have you back. And if this is your first time, welcome. Even though this is a specific webinar with a specific application, we will go over all of the bases of MultiMech before going in depth. This is a particularly exciting webinar because it is also being hosted by one of our customers, Fortify. Not only does Fortify provide a fantastic use case for our software, we're also given the chance to help a fellow startup company disrupt a very high-profile industry, additive manufacturing. Before we start the webinar, you should know that we'll be doing a question and answer session at the end. You can see on your Zoom application, you have a Q&A button. At any point throughout the presentation, you have a question, whether it's about a certain slide or regarding any of the core technologies being talked about today, feel free to write down the question. You don't have to wait till the end and potentially forget about your question. So as many questions as you want, please, we're gonna have a good discussion at the end of all this. Now, without further ado, let's begin the webinar. Presenting today is myself, Hayden Cornwell. I am a solutions engineer at MultiMechanics. Basically, what I do is a customer has a interesting engineering problem, and I help with using MultiMech, our software, solve that complex engineering issue. And I am based out of New York City. Dan?
Hi, everyone. My name is Dan Shores. I'm a co-founder and the software lead at Fortify. We are a 3D printing startup out of Boston, Massachusetts. Glad to be here today.
All right, looking at our agenda. First, we'll do an overview of MultiMech, which is the flagship product of MultiMechanics. Well, then Dan will give us an overview of Fortify and their 3D printing technology. We'll then go through a microstructure introduction and just do the basic steps for creating a microstructural model through MultiMech. Then we'll go through some studies that have been performed by Fortify using MultiMech, and we'll look at some slight DOE studies that have been done using our software. We'll then go into a multiscale example where Fortify actually looked at a part that was being made and how they incorporate MultiMech into that global level part. And then, like I said before, we'll have a Q&A session to wrap it all up. Okay, let's look at MultiMech. So what challenge are we trying to solve using MultiMech? And that's basically failure prediction. Engineered materials is extremely hard. When I say engineered materials, I do talk about complex composites, like your fiber reinforced polymers, with different orientations, really complex materials at the microstructural level. But any material really at some length scale is an engineered material. Like even a metallic alloy, at some length scale, you're gonna have inconsistencies, inclusions in your material that, although can be represented as an isotropic material, there really is some non-homogeneity throughout that material. So basically, is it possible to do this? And it is, but you have to look at where damage starts, and that starts at the microstructural level. You have a lot of microstructures start to accumulate damage, whether it's cracking or crazing or other forms of microstructural failure, and that slowly accumulates, and that leads to catastrophic failure at the global part. And when we look at this, it truly is a multi-scale problem because you start at the microstructure and it progresses through large structures at vastly different length scales. So what is the true multi-scale technology that MultiMech has developed? This is basically a way for us to look into the microstructure. And when we're doing a global level solve, we're also solving for the microstructure at the same time in a fully coupled fashion. When I say fully coupled, there's a few simulations we're going to show that really help illustrate what we mean by that. Right here, we have a gear and it's being loaded. The blue represents stiffness reduction. So that's basically the elements that are beginning to fail. Now, if we zoom into this microstructure, we're going to look at 3 different areas. So you see the same microstructure, But as we begin to load it, you start to see some cracking develop in different ways. This is just a way of showing that every single element in this global gear part is being represented by another microstructure independently. So if you have failure in one area, it's not going to be the same through other parts of the global level part. This leads to a more accurate solution because you actually see realistic failure progressing. Now, it seems like a very computationally intensive method, and it used to be. This is what I was just describing was the FE squared methodology, basically having finite element models within a finite element model. This simulation specifically without MultiMech would have taken 1,140 hours to run, so a month and a half. Using MultiMech, we got this down to only 40 minutes. So an obviously drastic, drop in computation time, but also the memory. This would take 1.5 terabytes of RAM previously, and now it only takes 5 gigabytes of RAM. So you can run this on a standard laptop. Another simulation that shows what's going on in real time. We see here we have a leaf spring that's made out of a unidirectional composite material. And as you run the simulation, you can see how the RVEs are being loaded simultaneously with the part. You can see some parts are under compression, some parts are under tension. And on that third RVE on the right, we can see some damage trying to develop within the resin in between the fibers. And you start to see how damage begins to evolve and how if you develop failure in some certain areas, the stresses begin to migrate to other RVEs, load those appropriately, and then they fail. So it's how you show progressive failure within a part, which gives it our high accuracy. We have partnerships with ANSYS, Dassault, and Siemens because we don't necessarily want to replace the current simulation softwares that are being used for part level. We think those are great and they do a great job of simulating mechanical performance. What we want to do is we want to enhance it. So we develop these partnerships so we can create MultiMech plugins, and we can help give more sustenance to these simulations that are being ran with these different tools without disrupting the engineering workflow of different companies. And specifically today, we're going to see some glimpses of the ANSYS plugin from MultiMech. And now, Dan will give us an overview of Fortify.
All right, so Fortify is a 3D printing startup based out of Boston, Massachusetts. We got our roots from a lab at Northeastern University where we were researching how to align fibers in a resin-based system, trying to get the ultimate strength and optimization of your alignment systems for composites. So this naturally progressed into 3D printing, and the company was spun out in 2016 on the principle of creating 3D printers, creating the software for them, and creating the materials for these systems as well that will print composite parts. So we've been running with that ever since, and here are a few of our prints that we've made pretty recently. Definitely high resolution and high heat resistance. And really happy with these parts that are coming out of our printers. So right now we're a pretty small team, very multidisciplinary. We have really strong minds in material science, hardware development, software development. Some really strong customer use cases recently. We see a lot of our customers using our parts for prototype injection molding tooling. This is an application where you really demand high heat resistance, really strong, stiff parts in order to get a lot of cycles out of these parts. So we've seen some cases of customers getting well over 100 cycles of their plastic injection parts from these cases. I'm really happy with that. We also have a lot of applications in automotive and aerospace, where again you require high temperature resistance and strong parts. The inner UAV components definitely need to be lightweight, so we're able to have the same strength that you would with a standard case while reducing the weight. We've had a lot of good reception in the past few years. Most recently, we were named the top 3D printing startup in the world at Formnext in Germany. And as a startup, we definitely value our venture capital partners. Right now, we're running off of our Series C and are immediately in the process of raising our Series A. So the Fortify platform revolves around digital composite manufacturing. And what that means is you're taking the high resolution, the high complexity of 3D printing and applying that with the high strength and heat resistance of composites. So the process starts similar to most any other 3D printing process where you create a CAD part. You could do the CAD design and you import that geometry file into our Inform generative software. And the main goal of the software is to determine the optimal fiber alignment at each voxel of the print. Once you have that orientation mapped out, it then exports your file package to the printer. We've designed and made our own printer in-house. It's based off of a DLP style 3D printer. And we add a number of different components that allow us to process composites, mainly a magnetic system around the reservoir. One of the most common questions that we get is, if you guys are working with carbon fiber, glass fiber, et cetera, how are you aligning them with magnetics? They aren't naturally magnetic materials. And that really dives into the development that we've done on the material side. So we are able to functionalize our fibers and our inclusions in order for them to be magnetically responsive. So when they're in the reservoir, they're aligning with the magnetic fields that we place on them. And that allows us to have complete control over the orientation throughout the part. So what this creates is high resolution, high strength and stiffness, and really heat resistant parts that we're very proud of. So to dive a little bit into that software that I talked about, when you import your model, you can choose to either import it along with FEA results or just import it just with the model itself. We'll take the stress data as well, or the topology, and we'll determine the optimal fiber orientation at each voxel of the print. So what that means is that each individual 3D pixel has a unique fiber orientation. And this allows us to have complete control over the microstructure throughout the entire part, giving us really good strength resistance abilities. So if you look at this part in the middle, if you were to imagine compressing it from the top and the bottom, what you would want is for your fibers to be oriented along these beams vertically, kind of following the curvature of those 4 beams. And that's exactly what you're seeing here. Referencing that 2D color map legend on the left. Anytime it's pink, it's kind of oriented out of plane, blue in plane, and the lighter sections are aligned perfectly vertical, and as it gets darker, it's becoming more horizontal. So this is exactly what you expect to see from a part oriented with fibers. Once we have that model, we can then export it to the printer in a fairly standard way that you would see with most 3D printers. So we slice the part, and you see 3 slices on the right that represent a single layer of the print, in this case, holding the alignment information along with it. So this, along with some other machine instructions, are sent to the printer, and it will print your part out. So we got printing down pretty well, but one thing that we struggled with early on was how do we simulate the parts that we're creating? How do we take these complex microstructures and determine if we're actually adding a significant increase to the strength? And that's where MultiMech came in. They pretty rapidly solved that problem for us because they focus on chopped fiber, and they're able to align these fibers throughout the simulation. So in getting into conversations with them, it became pretty clear early on that there were 2 great avenues to use their product. The first was in material development. So we're able to run design of experiments on a large number of different RVEs and materials. So essentially, we're adjusting variables such as fiber length, diameter, orientation, the volume fraction, even interface properties and matrix properties. And we're able to adjust these variables and compare them to each other, set up the DOE, and just run it overnight. So I think in one case, we had well over 80 simulations, all within MultiMech GUI standalone. Over 80 simulations that I set up, had it run, came back the next morning, and everything was complete, and you have this wealth of data that you can pull a lot of information out of. And it really helps drive where we want to spend our time, what's going to make the biggest impact to our material development. And secondly, we wanted to see how the actual part itself will be improved by our complex microstructure. So if you think about that sphere type part in the past slide, that's something that you could not, or be almost impossible to simulate with ANSYS alone, or any FEA software. And so MultiMech comes in. We have a nice little plugin for ANSYS. You can import the fiber orientation file and simulates it pretty simply. We'll talk about that a little bit later in this webinar.
Thanks, Dan. So yeah, I think everyone can see why we were so excited to be able to partner with you. It's a really, really cool technology you guys have here. All right, let's get into the microstructure introduction. We said a lot of really cool, interesting things here. Let's actually show the process and dig in a little bit and see just how we actually simulate it and show some results too. So looking at the MultiMech user interface, this is how you create a microstructure. And this is a user interface that was made by material scientists for material scientists. A lot of times with FEA, it gets really complex. You have to do a lot of mesh convergence studies, time step reduction, blah, blah, blah. It's, all the microstructure you can make have to be made by hand through different CAD softwares, and then you have to mesh it. It becomes quite a chore, and a lot of times organizations you have to pass this model in between different specialists. So we wanted to make a tool that was more focused for the material scientists looking at these new advanced materials and quickly run global scale simulations. So our workflow is pretty simple. You define a geometry, you choose your materials, and then you run the simulation. Before we get into the demo, we'll talk a little bit about some of the variables you can tweak within the software. When you're looking at the geometry, you can assign your volume fraction, you can look at your fiber alignment, and you can also insert the fibers randomly, and you can have the same microstructure, but have a different random insertion, so you get different results. You can then assign your material models, whether that's linear elastic, isotropic, orthotropic, whether you have plasticity, whether you have viscoelasticity, which MultiMech does a lot of work in. You can assign the material models and run your simulations accordingly. And then with the different tests you can do simple homogenization. You can do some generic loading tests, and you can also run a full multiscale. And we're not taking any shortcuts when we're doing all these full multiscale. We're directly solving the RVE. So there's no assumptions like mean field or anything like that. No analytical formulations are used. It's all doing direct computation. So let's do a little demonstration. Here is the MultiMech graphic user interface. Like I said, we have geometry, materials, and conditions here. Start off in the geometry. You have the option to import models. So if you have a microstructure that you want to use, go ahead and import it. We can import different RBEs, and you can assign the materials accordingly. To create a microstructure, you open the microstructure geometry dialog box, and this is where you change all the different parameters. So first we select our space. Is it 2D or 3D? Then we get into the type of inclusion. And we showed a lot of chopped fiber here, but you can really do a whole lot of different inclusions, whether that's sphere, ellipsoids. You can make them voids as well, and woven structures. Quite a lot of different structures you can do. Select the volume fraction. So in this case, we'll do 10%. You can select it's continuous. In this case, it's a chopped fiber, so it'll be discontinuous. Select your diameter length. You can have a random distribution of lengths or fibers. So if you select a max of 120, you'll have a random distribution of fibers from 120 to 100. And then importantly is the orientation. A few different options. You can go completely random, insertion of the orientation of the fibers, or you can make them completely unidirectional, which is what Fortify does. They align them perfectly in a certain direction. And then you can also do normal distribution where you have a principal direction of the fibers, but you can have some slight misalignment along the different axes. And there's also a tensor. So if you have info from a Moldex or a Moldflow 3D file, you can import the fiber orientation tensor. After you select these different parameters, you select the mesh button up here, and it'll automatically mesh and create your geometry. So in this case, we have a random RVE, a randomly aligned chopped fiber RVE. You can look at the orientation and see if it's to your liking. If you end up with a microstructure you like, you can go and select the green checkbox, and then now your microstructure will be uploaded to the GUI. After that, the regions that you made will automatically be available. So now we have matrix and inclusion regions that are automatically generated. Now we create our material properties. So in this case, we want to create a matrix and a fiber. Both these cases will be simple, isotropic linear elastic, but you can create a matrix material and then a fiber material. Simply designate those to assigned region, move on to conditions, select some local boundary conditions. Then you can homogenize your part, so you can see the linear, the homogenized properties. It'll tell you if it's isotropic, transversely isotropic, etc. And you can also run virtual tests. So if you have more complex damage, you can run uniaxial loadings and run it till failure. You can look at the stress strain curve, analyze things like toughness and strength of your material. So that's basically it. We went through a full process of creating a microstructure. It's pretty straightforward especially when we only use linear elastic materials. When we start incorporating failure, this is where MultiMech really separates itself from other type of microstructure generation tools, is that we can implement failure. So if you have certain resin properties, when you're solving this RBE, it's clearly dependent on the constituent material properties that you have. We can incorporate continuum damage into the resin. We can also do fiber resin debonding, which we're seeing here. That fiber resin debonding leads to resin cracking, which you can also see here. And then we also have general failure models that are used in other FEA tools. So we have a lot of things you incorporate here. And when you run this, you're actually getting a really good picture of what the RV is going to do when you load it appropriately. You can also use this RV in a large scale structure. So you can really accurately see, am I getting damage, and where is it occurring in my part? And this is something that really separates us from other types of tools. One more time, because everyone loves seeing the damage develop in this RBE. All right, next we're going to actually go into specific studies that have been performed by Fortify using MultiMech. Some variables of interest, one of which is fiber alignment. This is something that Fortify can do and actually control. So this is a rather important variable of interest in our microstructure. We can use different orientations like random, as you can see here. You see slightly misaligned and perfectly aligned. You can see when you go from random to perfectly aligned, how much more even the stresses are, and how there's no stress concentrations. Even in the slightly misaligned, you start to see some stress concentrations on different parts of the fibers. Fiber volume fraction, something else you can control. You can see here we have a higher volume fraction. See here we have a lower volume fraction. Then finally, randomness seed. This is something you can use where you had the same volume fraction in the same microstructure, except that these are inserted different random orientations. So you can see these all have the same volume fraction, but we have a grouping here, so that might lead to stress concentrations in earlier failure. And what this means, you can run multiple tests and actually get different results. Looking at some results, this can be viewed within MultiMech as well. You can see how through the chopped fiber, we have some fibers bearing a lot of load and some fibers not bearing a lot of load, which means that the resin around it, which is the failure point in this material, is starting to bear the load. So not necessarily ideal. We have the transverse properties, which see it's a little more even here, but that, it's not really much a high stress in the fiber. So that must mean that we're getting more stress in the resin, and specifically the fiber resin interface. Then we look at the perfectly aligned results. We can see how nicely the fibers are being loaded evenly. A lot of the stress is passing through the fiber, which means there will be a higher performance part. So you can see this all wrapped together. The last step, you can see how why a random fiber is going to be stronger and stiffer than transverse, but you can also see why the perfectly aligned is going to be superior to both of those by the way that they're aligned. So this is just kind of a general why we want to align fibers, and this is a big issue when even if you're doing injection molded, you're going to have areas that are going to have high alignment, and some areas are going to be completely random. So that's something to factor in when people are doing, doing manufacturing with these types of materials.
Yes, thanks, Hayden. So this is one of the DOEs that we ran at Fortify. Just to go over it quickly, so we're locking the volume fraction at 10% and really focusing on the alignment and the randomness seed. So as Hayden said, it's pretty clear that you're getting significant increases to your strength and stiffness through longitudinal alignment. And that's really why we do what we do at Fortify. We're really focused on getting as perfect alignment as we can. So you're getting well over 2x increase over your neat resin, and still a significant benefit over your random and transverse alignment. So the difference between us and a lot of different companies doing similar things is the fact that we're able to get fairly true longitudinal alignment, whereas many people are working in the random alignment regime. You also see the really cool effect of randomness seed in this. This data looks kind of like you would see in an experimental data set. For each sample of each alignment, we're changing that RVE mesh, and from that you get different RVEs where maybe the fibers are a bit more grouped together in some cases, or there's gaps in other cases. Essentially, you're trying to replicate as close to possible what you would see in real life. If you're running your DOE, assuming a purely dispersed fibers or perfectly homogeneous RVs, you're really not getting the full benefit of these tools. You're really able to find the best and worst case of each regime. So definitely a powerful tool. We're really excited about.
So we focused a lot on the microstructure, but you're not making microstructures here when you're actually selling to customers or creating parts. You're creating global scale parts on the order of millimeters and meters. So that's where multiscaling comes in. So we'll go over how MultiMech integrates with ANSYS. And you can run a fully coupled simulation for multiscaling with MultiMech standalone, but we find that a lot of people like to use the plugins because you already have your model in ANSYS and it's already ready to run. So what we have here is a workbench workflow. This is more of a complex one for composite parts. We're including ACP for any pre-processing and post-processing. We have the static structural model right here. So we're trying to show how does MultiMech fit in this workflow. So you see right here, we actually have our own module that allows you to create your microstructure materials. And within there, you can create your own library of RVEs and microstructural parts, and you can create it through the GUI that we just showed you. So you can open that up, open a window, and you can create as many microstructures as you want. Within the model tree within static structural, you can see that we have the MultiMech icon here, and that allows you to do more global scale options, like Dan will talk about in the next few slides. We have a fiber orientation option. We also have output options. So if you have an area of interest in your part, you can request output and see that RVE, and you can do that before or after the simulation is run.
Yeah, so here at Fortify, we use this S-hook as a case study. So I kind of wanted to share this with you guys, share the process of doing what we do at Fortify, as well as how we interface with MultiMech. So this geometry, fairly simple S-hook. You can imagine hanging some weights from it. For instance, we've gotten some cool videos and actually printed these parts quite recently. So here we're looking at like a worst case loading condition, right? So I set up the boundary conditions kind of on the extremities of the S in order to really see strong stresses throughout the whole part. So we run this analysis in ANSYS just as a homogeneous isotropic material in a static structural case. We do that just to kind of get a sense of the stress field before we really do anything else. We can take that result and, like I said before, import it into our Inform software. So the result of that is what you see on the right. And this file is fully printable at this point. And to kind of reiterate the color that I was describing before, the chopped fiber is oriented kind of horizontally as you see it, where it's blue, vertically where it's pink, and at a 45-degree angle where it's purple. So you really are seeing the alignment that you'd expect from this case. It's following the curvature of the S as it travels through it. So like I said, we could print this part at this point and call it a day, but what we really value at Fortify is knowing the impact that we have on the part and being able to simulate it and get results from it. So we use MultiMech for that, obviously, and it's a really easy process to do. So we already have everything set up in ANSYS from that first isotropic study we did, and the only difference is we add the plugin, as you see here. Like Hayden described, you set up your RVE and import it. And so we create a fiber orientation file during our software process. So we just import that file on this bottom section. In our case, we create this file from the ANSYS mesh, so we don't even need to import that second mesh. But you're able to dissociate the two if you would like for your process. And what this gives you is essentially MultiMech is talking with ANSYS and figuring out how to align the RVEs throughout the print. So this is a great graphic representation of it, and this is what you get with every analysis you do in ANSYS. It shows you at each element what the fiber orientation will be. And Hayden, correct me if I'm wrong, but what MultiMech is essentially doing in the background when you run this analysis is it's taking that RVE that you created, that you see on the right, and it's rotating the 1-1 direction, the X direction, essentially to match that fiber orientation. It's doing that at each element of the analysis, which is really powerful and really applicable for us, since we're essentially doing that in physical space for each voxel of the element, of the part rather. So it's a really powerful tool that is definitely getting the results that we want from it.
Yeah, you couldn't have said it any better, Dan.
Awesome. So once we run that, this is kind of the comparison that you get. So on the left, you see our neat resin hook. It's experiencing 2% strain at the stress concentration in the top left. And once we add the fibers and reinforce it, that's what you see on the right. And that's only 1% strain. So 50% decrease of strain in the part, and you couple that along with the increased strength that you get as well, and it's really showing just why we do what we do, and the benefit that you get from aligning your part. One, just adding the filler, and two, aligning it in an optimal sense, reinforcing the part. So this is really easy for us to do for each part that we print. Makes a huge difference to kind of know exactly what benefit we're getting over just a regular printed part, and that's definitely the value that we get with MultiMech. It's been really helpful.
All right, thanks, Dan. Yeah, and before we get into the Q&A session, I'd like to kind of recap what we talked about and generally where we are. We've seen a few simulations done here and there with our with our tool, and we're applying that to these structures. But we're constantly making improvements on our software based on what 3D or what Fortify wants. So we really view this as more of a partnership, and we're going it together. And we've already made a lot of improvements to our software to help represent the microstructures being used by Fortify. So Dan, do you have any more comments on kind of where this partnership is currently, and where you see this partnership going in the future?
Yeah, sure. I mean, where it is now is definitely what you see in these slides I showed. Where it's going in the future, we want to make this a more streamlined process where we can really be running this for every single customer part that we produce. As we move on to selling our printers in the next year or two, potentially find ways to give this ability to our customers as well, so they can be rapidly seeing the benefit that they're getting with every single print that they do. Yeah, just really making sure it's a quick and easy process, and continually showing that what we're aligning is the correct orientation.
Great. Thank you. So yeah, thanks, Dan, for the presentation. I think everyone here has a better understanding of the technology being Fortify, and as well as MultiMech, and how we're working together. So I think we can go now into the Q&A session. We have quite a bit of questions to go through. So I'll try to go through them as quickly as possible. And these questions spur more questions. Feel free to jot them down there. Can never have too many. I think the first one's more of a MultiMech specific question. Is there a plan to provide MultiMech plugin for LS-DYNA? LS-DYNA is the high, the explicit version of solver. So the answer to that is we currently don't have a plugin for LS-DYNA. That's something that is being created currently. Right now we have 3 plugins. Each plugin is different and integrated new software, so it does take time to build up. Being a startup with only 11 people, you've got a lot of work. So LS-DYNA is in our roadmap, and that's something we look to work on in the future. But currently, we don't have that integration. This one might be for Fortify. Is there a particular material that Fortify recommends for prototype injection molding cavities?
Yeah, sure. So for the cavities, that's something that we print a lot of. So we, the answer is really I recommend our material for it. And I say that because we've developed a injection molding tooling material with one of our material partners, and that's what we're using. It's really great. It gets the job done. It's very heat resistant, very strong. I can't really recommend too much outside of that, just because I'm not too familiar with materials out there.
So on the same kind of path, talking about Fortify's material, what is the typical length of fibers that you have?
Yeah, it's a pretty big range. So our system and our ability to functionalize fibers is really applicable to anything that we get our hands on. So the boring answer is really any length. To give a range, it'd probably be from 50 to 200, 300 micron, though we can go larger and smaller, really depending on the use case.
Cool, thanks. This one might be for me. Can you read fiber orientation result files from injection molding simulation to prototype injection molded parts with their predicted molded fiber orientation? Kind of a tongue twister, but so you have like these softwares out there like MoldX and MoldFlow that as you flow material through injection molded part, you have different fiber orientation. And the answer is yes. You can import this in the fiber orientation tensor. Basically, along with principal direction, also defines the amount of misalignment. So you can have perfect alignment, or you have misalignment, and then everywhere in between. So when MultiMech does that, you can create a lot of different RDEs with different alignments, and that'll be created automatically with our software. You can insert those automatically. So it creates like buckets of alignment and then inserts into the part. You can run a simulation right after. So it's a very streamlined process that we have. In another one for myself, in the microstructural model, how do you model the matrix fiber interfacial strength? So as more of a general answer, we model it through cohesive zones. And when I say cohesive zones, we have a novel way of implementing cohesive zones into your microstructure. Generally with FEA tools, you have to pick some surfaces, create a cohesive zone beforehand, and you have 2 nodes that are attached basically, and then you have to separate them. Well, what MultiMech does is you can create that microstructure, even the microstructure that we just showed and the results that Dan showed. There's no cohesive zones, in the first few steps. there's only one node in between the interfaces. And what happens is once you reach a certain traction strength that allows for debonding, a node will automatically be inserted and the crack will automatically be inserted. So that's another benefit, is that these cohesive zones can be really tricky to insert by hand. So we do it all automatically. And that allows for cracking not only at the fiber resin interface, but it allows for cracking to propagate through the matrix itself or fiber. And that's something that, looking forward, we've done preliminary tests with different cohesive zones with the models Fortify has been using, but we're going to look into different cohesive zone models. For example, there's like bilinear laws that govern traction separation. Just going through the different questions. Here's a applicable one for me and you, Dan. Can the fibers cross the RV boundaries? So I'll start this one off, and Dan, you maybe finish off, see where we're at. But when we automatically create them, this RVE, right now we don't have intersection. And when we're trying to get these results be more approved, we're creating new RVs that have this intersection. So that is somewhere on the roadmap for between MultiMech and Fortify, is really solidifying these RVEs, and eventually in one of our next releases we'll have the automatic generation tool insert these fibers automatically and randomly, and also intersect the boundary. But yeah, we're getting close to that, and myself and Dan have been working together to increase this and see if this intersection is truly necessary in our models.
Yeah, definitely correct. And one thing to add, Hayden kind of talked a little bit about importing custom meshes early on during the GUI example, or demonstration rather. And so essentially you can take really any mesher and or even CAD program and create your own custom meshes and your own custom RVEs. So that's kind of been our approach as far as exploring, what's the impact of fibers crossing RV boundaries. And the MultiMech GUI is very receptive to those custom RVs.
Oh yeah, thanks for elaborating. This is a question that I think I've asked before too, regarding the Fortify, the alignment process. Can the Fortify process align the fiber in the Z direction, looking at the hook coordinate system? But yeah, I guess basically asking, can we go all three principal direction for alignment?
Absolutely, and that's what separates us from a lot of our competition. Since we have this magnetic system that is 3 dimensions, we are able to align the fibers in any direction in 3D space. Essentially, you just give it a vector and it'll align to that vector. There's a number of processing difficulties that come with aligning in the Z, fiber length and different considerations. But if Z direction is important, in a lot of cases it is, then you can adjust the system and adjust your material to allow for that. And that's something that we do a lot, and we're definitely very focused on that.
Yeah, so I brought it back to that image of that sphere, and we can see we have the phi and the theta orientation, which shows it's basically a heat map of like how is it oriented, and also showing the z-axis orientation as well.
Yep. Yeah. So this is just spherical coordinates, and yeah, we have full control over those.
Mm-hmm. This is not necessarily directly a question for you, Dan, but we can talk about different microstructures that you can eventually apply. Can the RV calculation and damage model be applied to metals? Also, can the software be used to determine mechanical properties of metal lattice structures, for example, honeycomb type structure? And this brings me back to this image here. First question, can we do metals? Yeah, of course we can do metals. We can do metals that are just isotropic. We can do plasticity in metals. You can do metals with inclusions, and you can simulate the different particulates if you have inclusions within a metal, if you want to go the multiscale approach. Looking at lattice structures, we currently don't have the automatic geometry creation tool for lattices. That's something that will also be released in a future MultiMech release. But you can create a microstructure, and we have a library of different lattice structures and even foam structures that can be used. And I thought it'd be interesting, Dan, to hear your opinion on this, because I see a a lattice structure right here that actually uses the structure. So in the future there could potentially be some application that goes beyond the chopped fiber RV and actually creating an RVE that is a lattice structure. And MultiMech can do, we're not limited to 2 length scales. You can go 3 length scales if you'd like to run that.
Yeah, lattices are very difficult. This particular one isn't really created with your standard CAD program or your standard slicing program. And I can definitely see the challenges on MultiMechanics side as far as simulating that. Hayden, definitely let me know if that comes out, because I'd love to play around with that.
All right, sounds good. Okay, so here's another question for you. How does the program determine fiber orientation of a 3D printed part? Let's say it was done by FDM method.
Yeah, so I mean, this is kind of diving into some of our proprietary software algorithms. But I guess as much as I can say is that it'll take your FEA data and run it through our algorithm, and pretty much determines at each voxel, what the appropriate orientation is. It's a very iterative process, similar to MultiMech. A lot of optimization as far as software speed and memory is involved with that. Yeah, that's about as much as I can say on this webinar. Definitely reach out if you'd like to learn more.
Okay, and another question for you. How do there's a question for you. How do fiber reinforced resin parts compared to other composite 3D printed parts on the market?
Yeah, so I think most composite 3D printed parts are fiber reinforced. As far as comparing Fortify specific parts to other 3D printed parts in the market, goes into a little bit what I was talking about before. We have the ability to align in the Z direction. A lot of the other composite 3D printers, they create fantastic parts, but they use FDM, which is an extrusion-based method. And because of that, your alignment is limited to the tool path of that printing head. So because of that, you're limited to the X and Y orientation for your fibers, as well as there's a lot of orientations that you can't do because you just physically can't move the tool, the head in that direction. So there's a lot of limitations as far as fiber orientation goes. In our case, we use chopped fiber. A number of those companies also use chopped fiber. Some of them use continuous fiber, and there's whole theories as far as the benefits of both of those. Also, we get the benefit from using DLP, which is a resin-based system. It's very high resolution. So if the slide's already up, if you look at that part on the right, that was printed with our system, and I think it really shows how fine the detail can get. Really smooth layer lines, sometimes just non-existent layer lines. Really tight details, about 50 micron resolution in the X, Y, and Z. So that's one of the biggest benefits, and our customers really appreciate the surface finish and the look of the parts that we create.
So I guess a question kind of for both of us is about actually a little more detail about measuring the fiber matrix interfacial strength. Computationally, what you input is either just a straight up strength for the cracking to initiate. You can also have an interphase region, so you have one element, and then you can represent the element through a material model, like continued damage to represent that failure just differently. But it's a good question. How do you actually get this? I myself have done a lot of research prior to MultiMech, experimentally looking at microstructural properties, and the interface is huge. This governs the properties of these materials. And doing this measurement, there's a lot of different types of measurement. Whether it's fiber pull out, micro droplet, single fiber fracture tests. There's quite a lot of things you can do, and a lot of times there's not great agreement between those. It takes a lot of work, manual work, as well as different expertise in that. And a lot of times we find that's not necessarily, if you get that interfacial strength, it's not necessarily truly representative. So we have a way of calculating this, and we do this through the optimizer that we have. The optimizer, and Dan touched on this very briefly, can run simulations overnight, without actually having to make changes to it. And what we'll do is we'll take an RV like so, and what we'll do, we'll run it through optimizer, and it'll actually change the fracture properties of the FEA code. And it'll change it until we calibrate on a certain value, and we can match that value to composite properties. So in the example of what we're looking at for this specific type of material, the fibers that Fortify is using and the resin they're using, what we do is we can take some standardized tests, whether that's 45-degree alignment, 0-degree alignment, and 90-degree alignment. We can take that data there, and we can run it through the optimizer, and the optimizer will automatically run hundreds of simulations, tweaking this parameter, converging on an optimal cohesive zone parameter. And that's a way we find a lot of people are really interested in that, because this microstructure properties not only are not reliable, but they're also very tough to come by expertise. And I think that's something that myself and Dan are going to be working on in the near future as well.
Yeah, definitely.
Mm-hmm. This is an interesting question. Don't know if we have an answer to it, but how do you manage additive layer technologies in the RBE, in particular, in terms of boundary conditions to apply between two superposed RBE, one RBE by a layer? So this is a common question, a common topic when we're looking at simulating additive manufacturing. You go layer by layer. So you're not only going to have like your microstructure here, you're also going to have layers that are going to be potentially weaker or resin rich, or what have you. And the answer is we haven't necessarily created a best practices for this yet. We are somewhat new to the additive manufacturing simulation. This industry. So we're sticking with more of like the microstructure, but when we talk about the actual additive manufacturing specific properties, you can do anything you really want. It's FEA. You can build your microstructure however you want to represent it. If you think that there's a weak point in between layers, you can build a layer that has a different property. On the global level, you can build it layer by layer. You can have the automatic crack insertions within the model to simulate not only the microstructural damage, but the more mesoscale damage that you get. I don't know, Dan, if you have any opinions on this regard, or if that's a concern of Fortify, but that's kind of the approach that MultiMech would take moving forward if that was an issue.
Yeah, it's definitely something we think of. Inherent in any 3D printing process is going to be some layer funkiness. Generally, most DLP and SLA systems don't have as much of that layer weakness as you'd see in other systems. So for the most part, we accept that it exists and accept that the simulations we're doing in a computer are assuming perfect process production of the part. Like any FEA process, you have to understand the differences between theoretical and experimental, and be able to appreciate the difference and know how to react to it.
Yeah, thank you for that answer. We'll take two more questions here before we say our goodbyes. Another one for you, Dan. Let me try to find that question again. so I can read it verbatim. Are there limitations in terms of build size with the flux print technology?
Definitely. The limitations come mainly from the DLP technology. There are some leaders in DLP printing that are constantly pushing that, and specifically in DLP being a projector type. The optics industry is the one that's really driving, increasing that build area. It's something that we are constantly analyzing and making sure that we're on the bleeding edge of technology in regard to our build size. The specific flux print technology, which is the DCM technology that we're talking about for Fortify, we can adapt to really any size of a DLP printer. So the magnetics itself are not limiting what we're doing. So obviously, price changes involved, but overall, we're willing to get as large of a printer as we're able to. We have theoretical, simulations and designs that show that we're able to do that.
Great, thank you. Final question. This might be, I don't know if it's a question for MultiMech or Fortify, based on the wording, but we can discuss it very quickly. Does the Fortify process fully align the fiber at each RVE, or can you have a bias one direction? Sorry, I'll reread this. Can you have it biased to one direction, but still have a quantity of fibers in the other directions? So on the MultiMech standpoint, if you, sorry to cut you off, but on the MultiMech standpoint, like we said, we can have a principal direction of fibers and then misalign to different degrees. On the Fortify standpoint, Dan, what's your response there?
Yeah, so we try to run the simulation to be around the same size scale as our, voxel groups with similar alignment. So, in the case of what you saw with the hook, if we want to, we could align each individual voxel. In many cases, it'll be like, 3 by 3 by 3 cube of voxels or 5 or whatever. But yeah, for the most part, we definitely have the ability to, and almost always do align perfectly with that direction that's assigned to it. It's pretty rare for us to see any straying from that direction more than a degree or two. I don't know if that properly answers the question, but
No, that was great.
cool.
We are almost out of time. So firstly, I'd like to thank Dan for coming on to this webinar with us. I thought that was a great discussion that we had there regarding not only your technology in 3D printing industry, but how you can start incorporating simulation and specifically MultiMech into that process. For everyone listening, there will be a recording that will be sent to the email they used to register for this webinar. Moving forward, we also have some contact information that will be sent out. So if you're really interested in MultiMech or you're really interested in Fortify, you'll have a way to reach out, and as well as our websites and such. There was a question about if we'll be at JEC. I figured that would be a good good time to answer at the end. So MultiMech will specifically be at JEC. It'll be myself, Andrew Castro, and Christina Cathalo. Dan, will you guys be attending JEC this year?
I do not believe that we will, unfortunately. Definitely try to get there next year, though.
Okay, great. So I guess that's it. Dan, thank you so much for joining this webinar, and thank you for all the listeners.
Yeah, thanks, Hayden. Really appreciate being on here. Again, thanks everyone for chiming in, and definitely feel free to reach out to me with any questions about our product and our business case, and really anything you want. My email is open to you guys.
Thanks, everyone.